Swayam Prabha. Digital India. Educated India.
Welcome back. I am still Ramprasad Saptharishi. So this is going to be I'm going to show you a trick that I think many people have seen, but we will take a twist on it. We won't really be using it except towards the end. If people want to actually see this in action, we can. The reason is because this is a sort of card trick that requires two people, like to be in cahoots, in the sense that there's going to be a magician and an assistant, and then it's an effect involving that. Have people seen some version of a magician and assistant sort of trick before? You have? Okay. So let me tell you about this. Okay, this one is not. Let me tell you about this one thing which is called the 5-card trick. It's called Cheney's 5-card trick because this was first created by William Fitz Cheney. I'll tell you a little bit about the history of him as well. But let me tell you what the effect is going to be. So this trick is going to require a magician and an assistant. Okay. So to begin with, the magician is supposed to leave the room and the assistant now comes. And the audience is going to choose 5 random cards from a deck of 52 cards. Okay, this can either be random or this can be something that they decide to choose by themselves if you want. And this is what you give to the assistant. And what the assistant is supposed to do here is take one of those 5 cards, put that card face down. Okay, and the other 4 cards will be arranged from left to right in an order that the assistant wants to keep. So the assistant really gets to do only 2 things. First, of the 5 cards, decide which card to be hidden. And these 4 cards, you decide how you want to order them. Is that clear? And after this, the assistant leaves the room. So now the magician comes back, notices 4 cards on the table which are face up, and there is 1 face down card. And the magician is supposed to figure out what the face down card is. Okay, is the thing clear? Have people seen this trick before? Oh, I'm actually very surprised because this is actually a very, very popular trick. But let me tell you a little bit of history about William Cheney. It was surprisingly hard to find. So this trick apparently first showed up in 1950 or something. It was popularized by Wallace Lee in a book that he wrote called Mathematical Miracles. And it used to be called telephone stud because you could literally do this over the phone. You could call up the magician and say, hey, the 4 cards are this, 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 and this. And then the magician then says, okay, it's the 7 of hearts or something. Okay. So let me just go over the trick for you. So this is going to be a trick that involves a magician and an assistant. So the magician first leaves the room. The assistant from the volunteers are going to choose 5 cards from a deck. And the assistant decides which one of these 5 cards to hide and orders the other 4 cards. Okay, the magician now comes back. The only thing that the magician can see is that 4 cards in a certain order. And based on that, must figure out what the 5th card is. Okay. So this was called telephone stud because it was something that apparently you could still do it over the telephone. So William Fitz Cheney Jr. got his PhD from MIT in mathematics, and the article that I read this trick from said that he was the first PhD in mathematics from MIT. But the Wikipedia page for MIT mathematics does not seem to say William Fitz Cheney is the first person who was awarded the PhD. That's apparently some James Taylor. But I can understand that it's not like when you award a PhD to one person. It's probably going to be for a batch. So maybe he was in the batch, I don't know. But there's some conflicting reports about it. He then was a professor of mathematics in University of Connecticut. And he was also the dean for a long time and stuff. But as you can imagine, for all of these people, this is their day job. But most of the time, they're probably trying to come up with some nice, interesting card tricks and so on. So since I have to show you this trick, I need an assistant as well. So which means that You know how to do this, or oh, then I mean, like the whole point is you and I need to agree on some rules beforehand. So what I did was I did the what I could, which is to ask Claude to do this instead. So then Claude was for. So we're going to try out a demo with Claude, and let's see. I mean, hopefully I don't mess this up. Okay, let me tell you how this thing will, because I want someone to play the role of the volunteer. Basically, click the button twice. I'll just tell you how this is going to work. So when you press draw 5 cards, it just draws 5 cards. Okay, from a deck. And you should imagine this is what the assistant sees. Okay, and then the assistant is going to choose an arrangement. This is what the assistant will do. So it currently is showing you what card is hidden and how the cards are going to be placed. And this is when you are supposed to call me. So I get to see this, and I should be able to say that this is the 4 of hearts. I hope it's the 4 of hearts. Yes, okay. Okay, so this is how the thing is going to work. So of course, right now we just saw what the hidden card was. So you will see like, hey, you just, you sneaked a peek sort of thing. So I want someone to just come here and just do this. Tell me when I can look at the screen, and I'll tell you what. So I just need I need a volunteer. Okay, please come here. Okay, so the rest of you, here is what I want you to try and pay attention to. There is obviously a strategy here. Try to figure out what is it that I am doing. Like, you may not be able to figure out the entire strategy, but try to figure out what are something. We'll try out a few things. So you can just click on start again, just follow the instructions there. Tell me when it is yes, exactly. Yeah. By the way, the rest of you should probably remember what card was hidden. Yeah, thank you. Oh. Oh, I can look. That guy won't complain. Yeah. Okay. This should be the 4 of clubs. Was it right? Okay. Okay. Let's try a few more. Okay. Yeah. Actually, why do I need to stand there? Oh, good. Sorry? Okay. So it should be the 9 of hearts. Okay. Good. So we'll try one more. So I'll tell you. Okay. Let's maybe give it a couple more shots, so then people can. Oh. Okay. 9 plus 6. Okay, so it's a diamonds, and 9 plus 6 is 15 plus 1 16. So plus 6. 9 plus 6 is, yeah. It's 2 of diamonds. Okay, 2 of diamonds, right? Okay. So have people already figured out how this was happening? Okay. So, let's just try a few things. Can you just try to figure out what the last suit is? Okay, good, great. So you figured out that the first suit is the same as the last suit. Okay. And what about the number? Good, excellent. Yeah. Okay, I'll call you again when we do the more complicated version of it. Okay, but you've already gotten a. Okay, you've already gotten most of the thing already. Okay, so let's just go over how this works. Okay, does someone want to explain how the trick works? I mean, like you.
Can we see the examples again?
Sure. Okay, I'm just drawing 5 cards.
So do we have another example after?
Okay.
Isn't there a chance that you can choose one, right? That's right.
Okay, so I think you have the full strategy already. Oh, okay. Anyway, we'll see. Okay. So let. Okay, let's try to think about how much ever you can. So, okay, what was the assistant doing here? So, can you, yeah, what was the assistant doing? Huh. Yeah, go ahead. Huh.
First and the last card is the same.
Okay, so among the 5 cards, the assistant chooses 2 cards that share a suit. Why should there always be 2 cards that share a suit? Good. So this is also called the crow postbox principle, right? I mean pigeonhole principle. Yeah, whatever. Okay. So you find 2 cards. You find 2 cards that share the same suit, and somehow you should arrange these. Huh? No, but then choose 2 diamonds. Just two. Assistant is choosing the card. Right? Okay. So this was the, whatever I have described here is the original strategy that Fitz-Cheney came up with, which is basically what you said. We have 4 suits. We have 13 cards in each suit. Right? So 5 cards are chosen. So therefore some suit must repeat. It can repeat more than once, but at least it can't be 5 different suits. There's only 4 suits. Okay. So the first card and the hidden card is supposed to be the same suit. So from the magician's point of view, by looking at the suit of the first card, the magician already knows what the suit of the hidden card is. It's just a question of which card it is. Okay. And the idea is to order the remaining 3 cards such that you somehow signal the value of that card to the magician. How many orders are there among 3 cards? How many ways can you? There's 6. Okay, the magician has already seen 1 card. There are 13 cards of that suit, which means there are 12 possibilities. You are only going to give me 1 and 6 of them. So you are like, but wait, there are only 6 permutations. There are 12 possibilities. How can I possibly get this across to you? Okay, has someone figured this out? No, the color though you've decided, because that the suit was good. So okay, so I'm going to specifically give you. I'll give you something that is easily recognizable. Arey yaar, why isn't it? Oh. 8-6 king. Why am I not getting the ascending order? Okay, when I want it, I will not get this stupid thing. Okay, so let me just tell you how the thing works. Okay, the whole point is going to be that when there were two cards that repeated, the assistant gets to choose which one to place and which one to hide. So technically the assistant has two choices more. Yeah, so with that we'll figure out exactly how that's going to work. Okay, so I'll tell you what I was doing. So obviously we need some mechanism by which when you see a permutation of those other three cards, I want to somehow go from there to a number. So there are 6 permutations. We need to come up with some way of saying this is permutation 1, permutation 2, permutation 3, etc., etc. So the way I'm going to do this is the following. We will always say that, it's easier to look at ace through king, just look at the number itself. And if you're breaking ties, breaks ties according to, alphabetical order. This is clubs, diamonds, hearts, and spades. It's just, alphabetically it's easier for me to figure out. You can come up with your own mechanism to do this. But most of the time, let's just hope that numbers don't repeat. So it's easier for us to figure out what the order is. Okay? And when I have 3 cards, the orders are of the form low, middle, high, middle, or middle, low, high, or middle, high, low, or high, middle, low, or high, low, middle, etc. Each of them I have just given a number. Okay? This is my mental modeling. If I see cards in ascending order, that is permutation number 1. If I see cards in descending order, that is permutation number 6. Everything else in the middle, there is some number associated with it. Okay? With this in mind, let's go back to our thing and figure out what was it that I was doing. This is repeating. This is also repeating. Okay, let's just do this. Okay? So let's figure out what, let me write down all the permutations on the, A is 1, A is 1, okay? So low, middle, high, low, high, middle, middle, low, high, middle, high, low, high, low, middle, high, middle, low. This is 1, 2, 3, 4, 5, and 6. Okay? So basically what, this is permutation number. So this is high, low, and middle. So that's permutation number 5. Imagine adding 5 to 8. What do you get? 13. So the last thing has to be the king of spades, king of hearts. Okay? That's the ordering. Okay, now you are playing the role of the magician. Okay, now so clubs is before diamond. So it's actually middle, low, high. Yeah. So jack is like 11. Yeah. Okay, so jack was 11. 11 plus the third thing. So 11 plus 3 is like 14. But 14 is like after king, it becomes ace again. Okay? Do you want to do one more? So what should this be? 5 of clubs. Had these two been swapped, what would this be? If it was 10 queen and 11 4 of clubs. Perfect. Okay, so now you know how the thing works. Okay, but let's ask ourselves, sorry, if these two were swapped, then the permutation is low, middle, high. So that should have been 3 plus a 1, which is 4. Okay, so had it been a 4 of clubs, that's what the assistant would have done. Okay, so this is how this works. Okay, good. Okay, so this was the ordering that we had in mind, and I'm just thinking of ace through king in this thing. So for example, suppose, these were the cards that were there. This is 4 plus, what is this? This is middle, high, and low. Middle, high, and low is 4. So 4 plus 4, this should have been the 8 of spades. All good? So now you could ask, what if the 5 cards were this? 4, 3, 6, 2, and ace. Because if I keep 4 here, how much do I need to go to ace? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't have the 10th permutation. So now what you do is you put ace of spades as the first card. Okay, so then you are 3 steps away. So you take the third permutation and you order the remaining. No, like you take a card such that the other card is within 6 steps from you.
So worst case is 6 and 7, you pick 6.
Worst case is actually ace and 6 or something, or ace and 7 or something. That's the worst example, in which case this way it is it's too many, but on the other side no, or this way it is just barely okay. But if it was ace and 8, you will instead do this. Okay, this is basically what's happening. And the only thing that is being used here is the following. Because we have 13 cards, one of them is already chosen. You can reach any other card either via the right side within 6 steps or via the left side within 6 steps. So you just choose the thing such that from that card within 6 steps on the right side, you get to the other card. So that's what the assistant is going to be doing. Is this okay? Isn't this a cool trick? I mean, it's a great trick to show people. But of course, you and an assistant both need to decide on figuring out this order mentally and coming up with this number and so on. Okay, so we've spent about 25 minutes on it. So clearly there's 25 minutes more in the... Huh? No, this is not done. Okay, so here is, I want to extend this a bit more. So, but one thing we should be very, very thankful for this thing is that thank God there were 4 suits, because had there been 5 suits, there won't be a repeat and we are stuck. And thank God there are 13 cards in a suit, because had there been 14 cards, then the problem is something would have been 7 steps away from both sides. Then again you are stuck. So it just so happens that because our deck has 52 cards, which is 4 times 13, this trick just works out perfectly. Okay, but some of you should be wondering, okay, this was one strategy, but maybe there's a different strategy. Suppose we had jokers in our cards. Would that work? So what if we had 53 cards? That is, I had a joker also. Or what if I had 60 cards? Or 80 cards, 100 cards, 200 cards? At some point, this should stop working. At what point does it stop working? Okay, how many people think 53 is optimal? That is, 52 is optimal. With 53 cards, we can't do. I mean, again, I'm not asking you, you don't need to know the answer, just your gut instinct. You think 52 is optimal? Okay, good. How many people think we can do 60? No, we'll just think of cards as numbered from 1 through whatever. We will come up with some strategy. We will say the first 13 cards are this suit or whatever. Okay, 52 optimal. I have some, 5 votes, 5, 6 votes. Okay, how many people think 60 is doable? 5 cards. Yeah. It's still 5 card, hide 1 card. Sorry, 1 second. So we'll just call the cards numbered from 1 to whatever. No, not 2 decks. We just think of them as like different unique cards. We'll just number the cards from 1 to whatever. No, we are still playing the 5 card, 1 hidden game. Okay, 52 is optimal. 52 is okay. Are there anybody who thinks 60 is doable? Okay, there are a few people. Among those people, do they think 80 is doable? No, but if it was, you're saying a million cards is doable also? Like in a million cards, if... Yeah. So the point is, you should also remember that, from the magician's perspective, the magician is only going to be showing you 4 cards. Somehow that should give you the identity of the 5th card. So obviously, if the deck was like a million or 10 million, This is just not possible, right? Suppose you only see 2, 3, 4, 5 in some order. I mean, the best you can do is like, there's some bound on what all you could have possibly seen. So definitely too high a number is not possible. But it's just a question of, do we think we can do 80 or 100 or 200? What's the correct number? Like, what is the N for which if we do Chinese, take 5 cards, hide 1 card away, this is actually possible for a magician and an assistant? No, even if you did that, so suppose there are only 24 possibilities, right? Okay, so let's try to work this out.
No, because you still are hiding only three. You still picking for five.
Okay, would you be impressed if I showed you this trick for more than 100 cards? Okay. Uh, okay, so I want your help again uh, to just do this clicking. And this, I really hope I get it right. I mean, this is not going to be easy, but anyway. Yeah, you can draw again. So what we are going to do in the remaining time is to show that we can do this with 124 cards, and that's the maximum. You can't do with 125, but anything less than 124 you can do. Okay? And we'll figure out why 124. What is this number? Yes. I mean, you just call the Joker as the 53rd card. It's just a number. There's no suit. Just think of it as card number 53. Like, for example, rather than it being clubs, hearts, spades, and diamonds, suppose the cards were just called 1, 2, 3, 4, 5, all the way till 52. No, there's no suit. I mean, suit is just a way for us to identify a card by using 13 and 4. But you could just call it 1 through, let's say, for example, if number 1 to number 13 is hearts. Number 2, the same strategy won't work. It has to be a different strategy. And I will show you what strategy works. Okay? So, okay, I'm not going all the way to the back. I promise I'm not seeing. Oh, okay. Let's see. Uh, four, 6, 8, 9, 45. Let me just confirm. Uh, 1, 4, 6 plus 6 plus 2 is 8 plus 1 is 9. That is 45. What is it 49? Okay. Okay, good. Okay. Do you want one more try to just so that I'm not cheating? Okay. Okay. So 3 plus 2. 12 plus 2 is 14. 17. 12 plus 2 is 14. 14 times 2 is 70. 72. 73. 74. 74? Okay. Okay. So this is clearly doable, hopefully. What, one more? Okay. That guy really doesn't trust me. Okay. Okay. So there's 1. So is it right? What is happening? That's 1. And this is 23. 23 times 23 times 120, 115, 116, 118, 119. Is it 120? Okay. Okay. Good. Okay. So hopefully now you trust me. And if the demonstration wasn't helping you, I'm going to tell you how I did this. So that, okay. And the nice thing about it is that everything that you need to figure this out is something that you have seen already. Like in your previous lectures, etc., you saw what graphs were, you saw what matchings were, and we are going to use graphs and matchings to come up with a strategy for this. Okay, so let me remind everybody of what these things are. So this is a graph. A graph is, I mean, like, in mathematics, we think of graph as, I don't know, x squared, x cubed, etc. But oftentimes in computer science, when you're thinking about graphs, it's basically vertices that are connected. There are vertices and they're connected. This is a special graph which is called a bipartite graph because it looks like there are two parts and edges are only going from part 1 to part 2. Okay, this is an example of a bipartite graph. And can someone remind me what a matching is? Yeah. Sorry, can you? Good. So a matching is just a collection of edges that don't share endpoints. Okay, such that there's no common vertices. Like for example, an example of a matching is whatever is written here in yellow. Okay. Now we will say this specific matching. We will say this matching saturates the left side. By which what I mean is everything on the left has been matched to something. Okay. And this is an example of something that does not saturate the right hand side because there is like this vertex that is unmatched. Is it possible for it to for there to be a matching to saturate the right side? Why not? Right. So obviously there cannot be a matching that saturates the right hand side because the right hand side has more vertices than the left hand side. So okay, so this is the thing. And something that's going to be very, very crucial, in fact, this is if people have heard about the P versus NP question in computer science ever, the whole class P came up because of trying to understand this one question. I give you a graph. Can you tell me, is there a matching in this graph or not? Like, what's the largest matching that's present in this graph? Okay. We are going to focus on something very similar, but we are going to focus ourselves on something that I'll call regular graphs. This is not really, there's some kinds of regular graphs. So here is an example of a graph where every vertex on the left has exactly 2 neighbors. And every vertex on the right has exactly 3 neighbors. 2 is not equal to 3, so it's not a regular graph. But this is something that we will call a biregular graph because everything on the left side is regular, everything on the right side is regular. Okay, this is an example of a biregular graph. And I don't know if you saw this fact in your previous things or something, but here is a fact that is there, which is that whenever you have a biregular graph, turns out there will always be a matching that saturates the smaller side. Okay? Have people seen this?
Have you seen how do you relate to the minimum vertex cover? Yeah, maybe.
Yeah, okay. So you can think about it. There are many ways of seeing this. In this specific example, this is a graph that is biregular. The right side is the smaller side. So you should always be able to find a matching that saturates the right side. Okay. Here is an example of one such matching. Okay. And here's maybe another matching. And here's maybe another matching. In fact, what we did was we actually covered the graph using 3 matchings. Okay. You can think about how to do this, etc. But it's just a fact that is true. Yeah, it is always possible to cover a biregular graph using exactly as many matchings as the smaller side's degree. Okay? Basically, because you find one matching that saturates the right hand side, imagine removing that matching. It will still be a biregular, I mean, actually, it's not quite true. It won't be a biregular graph because there are some vertices on the right whose degree is too large. But there is a way of doing it this way. Okay, anyway, the only thing that we will need here is that if you have a biregular graph, you will always find a matching. Okay, good. So now we are going to build a card. We are going to try and understand this Fitch's trick with n cards. So let's build this graph which has two sets. One of the sides is supposed to be what the assistant sees, and the other side is supposed to be what the magician sees. So the assistant is just given a set of 5 cards, right? Let's just imagine a graph where every vertex on the left hand side corresponds to one such set of 5 cards. Okay, like for example, maybe that vertex corresponds to the set being 36, 25, 6, 10 and 2. And maybe this vertex corresponds to 1, 23, 5, 1900, something, some set of 5 cards. And there are many vertices on the left hand side. So this is like what the assistant sees. What does the magician see? So the magician is going to see a specific ordering of 4 cards. Okay, so I'm going to put that in sort of like a round bracket as opposed to this curly bracket. When you're talking a curly bracket, I mean, like, you know, the order doesn't matter. But when I'm putting a round bracket, I'm going to insist that the order is relevant. Okay, so for example, 23, 5, 1, 19 is one such ordered set of 4 cards. It's possible that 23, 19, 1 and 5 is a different ordering of the same 4 cards. As sets, they may be the same, but as ordered tuples, they are different. So that's what is present on the right hand side. This is what the magician sees. Okay. Now let's just ask ourselves, what is now possible? So the thing is, the assistant is going to be given one of these, I mean, something here. The assistant is going to be told, hey, these are the 5 cards that you have with you. Now, what is the assistant allowed to do? Hide one of them and put the other 4 in a specific order. So basically, the assistant has to choose between either this configuration or this configuration. Right? That's what the assistant is allowed to do. Magician only sees this and is supposed to figure out what the hidden card is, which in particular means can figure out what those 5 cards are, because 4 cards the magician can see already. Is this okay so far? So let's just, from this world, what does a strategy look like? The assistant is given a vertex on the left. Okay? And you must now choose a right neighbor, which is the act of hiding one card and ordering the other 4 cards in a specific order. The magician only sees the right vertex and must somehow figure out what the left vertex is. So when is this possible? So what should a strategy be?
Each point on the right side must correspond to a point on the left side.
And must correspond to a unique point on the left side. What is the other name of that? So for example, we decide that, you know, when the magician sees 23, 19, 1, 5, the magician is going to guess, oh, the missing card is 100. So which means you put something like this. But you don't want a situation where, you know, something else also has the same edge here or something, right? So what are we trying to build therefore? So all we want here is actually a matching. So what we are going to do is, the strategy is going to be, we will pick a matching that saturates the left hand side. Okay. Now the assistant's job is just the following. You give the assistant a left side vertex, the assistant will just map it to the right side vertex. That's what is going to be put on the table for the magician. Now the magician will look at the right side vertex. Because it is a matching, it can be matched only to one vertex on the left. So the magician chooses that one vertex. That's it. So which means a strategy is possible whenever this graph has a matching that saturates the left hand side. In fact, any strategy corresponds to one such matching. So now let's do some calculation to figure out when can there be a matching. Let's first get a sense of which is the larger side now. Like how many vertices are on the left, how many vertices are on the right. So how many vertices are there on the left? NC5. Okay, good. So there are NC5 vertices on the left. I'm just going to write that down on the board here. This is n into n minus 1 into n minus 2 into n minus 3 into n minus 4 divided by 120. This is the number of vertices on the left hand side. All good so far? Okay. How many vertices are there on the right hand side? NP4. How many is that? So that is n into n minus 1 into n minus 2 into n minus 3. Right? This is what NP4 is. This is n choose 5. Now for there to be a matching that saturates the left. Oh, I swapped the left and the right now. sorry about this. So it better be the case that n choose 5 is less than or equal to this quantity. Right? That's the only way you can get a thing. So, okay. Can you solve this and tell me what that will be? 124. So basically, all of these guys get cancelled. So it eventually comes to something like n minus 4 better be at most 120. So which means that n definitely has to be at most 124. So beyond 124, we can't play this trick. I mean, this won't work because if the number of cards were more than 124, the left side seems to be way larger than the right hand side. So there's just no way of us to encode the information that we want for the magician to figure out the missing card. Huh?
Technically, we can say that if it's 125, then the one that does not have a match is 124.
But no, you're going to run into the same signaling problem. Think about it a bit more. So, okay, but this only tells us that definitely 125 and beyond we can't do. But we need to convince ourselves that 124 is doable, right? So let's first get a sense of, is this graph biregular? So we have just argued that the only way you can have a strategy is if there was a matching here that saturated the left side, right? For there to be a matching that saturates the left side, it better be the case that the left side has at most as many vertices as the right side. The left side had these many vertices. The right side has these many vertices. So for this inequality to happen, you must have n minus 4 to be at most 120. So you get n is at most 124. Okay? So now let's ask ourselves, how many neighbors does this vertex have? That is, suppose you are given 5 cards, how many different things can the assistant do? The assistant can choose any of the 5 cards to hide. Right? Once a card is hidden, the assistant can order the remaining 4 cards in any way they want. So there are totally 120 ways that the assistant works, 120 possibilities for the assistant, which means every vertex on the left has basically 5 into 4 factorial neighbors. So the left is regular. Correct? All good so far? What about the right? So if the magician sees cards number 1, 2, 3 and 4, how many possibilities are there for the 5th card? No. So this is, suppose we didn't have any strategy. So it's n minus 4. Of the pack of n cards, 4 of them you already see. So the missing card could have been any of the other cards. So there are n minus 4 of them. So which means every vertex on the left has that many neighbors. Every vertex on the right has exactly this many neighbors. So we are dealing with a biregular graph. Okay? And we just saw that because the graph is biregular, there is always a matching that saturates the smaller side. Okay? And therefore, we have a strategy for 124 cards. All that you need to do is come up with some mental picture of what this matching is. Now, obviously, you will be like, dude, all this is okay, but is this humanly playable? I mean, we need some strategy that you can demonstrate to somebody else. Okay? And in the remaining about, how much time do I have? Okay. So I'll take about 10 minutes or something and tell you exactly what was the strategy I followed. I'll give you as much of it so that you can reconstruct the rest of it on your own. Okay. So, oh, we just saw it in action. I didn't mess it up, thankfully. Okay, so here is a human strategy. Okay, I'm just going to call the numbers as 1 through 124. Okay, everything is just written up here. And let's, for the moment, put ourselves in the shoe of the assistant. Okay, and let's say that these are the 5 cards that were chosen. Okay, some set of 5 cards have been chosen. So here's what the assistant is going to do. The assistant, let's say the card numbers were I0, I1, I2, I3 and I4. I'm just calling those cards as I0, I'm calling it from 0 onwards for a reason. Okay, the smallest card is I0, the second smallest card is I1, etc., etc. What we will do is we'll add up all of the numbers and find out what's the remainder when you divide by 5. Okay, in this case, what is the remainder? It's like 4 plus 7 is 1 mod 5 plus 3 is 4 mod 5 plus 4 is 3 mod 5. So it's 3 mod 5. So eventually you should get 3 in this thing. If you add everything mod 5, that's what this number C is. What the assistant is going to do is hide the card IC. So if the C happens to be 0, we will hide the smallest card. If the C happens to be 1, we will hide the second smallest card. If C happens to be 2, we will hide this card, 3 this card, 4 this card. So is what card is going to be hidden, is that clear? So we are just, the assistant just adds up all the numbers mod 5. Whatever happens, hide the thateth card. Whatever, what you mean, you understand what I mean by that, right? Good. Now, and the other cards will now have to be rearranged somehow. Let's not worry about that for now. Let's put ourselves into the shoes of the magician now. So the magician sees some 4 cards in some order. We have not decided on the order. We'll figure that out later. The magician sees 4 cards. Now, what the magician will do is magician will try to do the same thing mod 5. So 4 plus 7 is 1 mod 5 plus 3 is 4 mod 5. This is 0 mod 5. So I get 4 mod 5. Now let's ask ourselves, what is the missing card? What can it possibly be? So even without any calculation, I know the missing card is not one of these 4 cards. It's one of these other 120 of them. So let's split them up as, it could be between 1 and 23, or it could be between 25 and 46 or something, or it could have been between 48 and 82, or it could be between 84 and 104, or it could be between 106 and 124. Basically, I'm saying it could either be smaller than 24, or between these two, or between these two, or between these two, or bigger than this. These are the 5 possibilities. Now let's ask ourselves, suppose the card was smaller than 24. What can it be? What are the possibilities? So can the card be 4? Suppose the card was 4. Let's put ourselves in the shoes of the assistant. What would the assistant have computed the mod as? That would have been 4 plus 4 mod 5, which is 3 mod 5. So why will the assistant have hidden the smallest card? Right? So for the assistant to hide the smallest card, the assistant must have seen a 0 mod 5. Otherwise, the assistant won't hide the smallest card. Right? Which means whatever the missing card is, it must be such that when you add that to this thing, you get 0 mod 5. So what can that be? So it can only be cards of the form 1 mod 5. So if the missing card was the smallest card, it's not like all of these are possibilities. In fact, the possibilities are just these. All good so far? Okay. Suppose the card was between 25 and 46. What are all possible? So the only way the assistant would have hidden the second smallest card is if the mod happened to be equal to 1 mod 5. 0 mod 5 was the smallest card, 1 mod 5 was the second smallest card. And the only way it can be 1 mod 5 with this is if this card was a 2 mod 5 sort of card. So the only possibilities are those. Now for same thing, for this it would have to be one more, so it will be 3 mod 5, and this one will be 4 mod 5, and this one will be 5 mod 5. So these are the possibilities. Even though it felt like there were 120 possibilities for the missing card, there's far fewer. Let's just count them. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. How many ways do we have to order 4 cards? Exactly 24 again. So 4 factorial is 24. So it just so happens that after we did this thing, there were exactly 24 possibilities. So far we didn't make use of the order at all. So the assistant will order it in such a way so that among these 24 possibilities, the assistant will tell you which one it is. If the 4 cards are arranged in ascending order, it will be the smallest of the possibilities. If the 4 cards are in descending order, it will be the largest of the possibilities. If the 4 cards are in order number 17, it will be the 17th possibility. So all you need is some mental way of sort of figuring out what this, from a permutation go to this, a little bit of practice, and then you can do this trick on your own. Okay. So just want to briefly recap so that everyone understands. It's a beautiful strategy. Okay. So let's just go back to, so what was the assistant doing? So the assistant was given 5 cards. So the assistant takes the sum of all those 5 cards mod 5. That will tell the assistant what to hide. Okay. Once the assistant decides to hide something, there will be exactly 24 possibilities that the magician will face. So you order the remaining 4 cards in one of the 24 ways. Okay, that's the part I'm not really going. I mean, it depends on some way of doing it. And from the magician's perspective, the magician computes this value and tries to figure out, well, if the card was the smallest card, what can it possibly be? So there will be a specific residue value, which will be like, in this case, it was 1 mod 5, so and so on. So it will cut down the remaining possibilities from 120 cards to just 24 cards. And then the ordering is exactly going to tell you what to choose. And with some practice, you can actually do this as a demonstration. Okay, great. So, so this particular strategy, yeah. Good. So I'll leave that as an exercise for you to figure out. They'll turn out to be exactly 24 cards. In everything, there will be precisely 24 cards. So this strategy is tight. If the deck had one more than 124 cards, it will not work. In fact, it's not possible to come up with a strategy for 125 cards, but you can. Okay, so this particular trick is by a person called Elvin Berlekamp. I don't know if people have ever heard of Elvin Berlekamp at all. In fact, when I learned that this particular, not the trick, the strategy that I just mentioned is by Elvin Berlekamp. When I saw this as the name for the strategy, I was shocked because my research involves a lot of what Berlekamp does, and I had no idea that he was actually interested in this sort of recreational mathematics as well. Okay, so firstly, thanks for this awesome strategy, and also for he's probably the most famous for his work on something called Reed-Solomon codes, which is used in a bajillion applications. Like for example, nowadays, we all use QR codes like happily. And the underlying ideas behind QR codes are basically something called Reed-Solomon codes. And Berlekamp and Welch's algorithm is a way of correcting errors, etc. Even if your QR code is slightly smudged and stuff, your phone is able to read it quite well. And there's a lot of error correcting code applications. That's what I knew Berlekamp for most of my thing. And these Reed-Solomon codes are also what are used on CDs and DVDs. In fact, it's also what was used when the Voyager spacecraft actually sent back an image of the pale blue dot. I don't know if people have seen that picture. It's again based on some Reed-Solomon codes. And I work in a lot of polynomial related computation, and I had heard his name on polynomial factorization, and all the polynomial factorization algorithms are due to him. And I learned in the process of creating this talk that he was a major activist for this recreational math. So, so there are people like Martin Gardner, John Conway, Berlekamp and all who sort of popularized this idea that there are mathematical things that people should study to again, for no use, but it's like, to get people interested in the subject and just get motivated to do this. And in fact, he was one of the people who started for this thing called Gathering for Gardener. And there's a bunch of people who get together and he posts puzzles, and there's so many puzzles that have come out of this Gathering for Gardener conference. And he has like so many contributions. I just can't. And I will also highly recommend checking out his Wikipedia page because it's really hilarious. I mean, like, so one of the things he says is that, he met his wife when he was juggling and he had to go and apologize to her because he was making too much noise in the apartment. so it's really interesting, this thing. Yeah. Okay. oh, good. yeah. I mean, like, read his technical contributions of it. Okay. So, by the way, I came across this entire article this entire strategy and stuff by this paper of Michael Kleber, where he basically calls this the best card trick in the world. Okay, and he in fact gives a full description of how you can do this mentally as a in a demonstration and stuff. And this is the 5-card Cheney version, but the paper also goes on to explain how you do the 124 version. And for my assistant, I mostly use Claude. I just told Claude didn't know the 124 card strategy. So I had to tell Claude, saying, Claude thought that, do you mean you want to take 6 cards and hide 1? I'm like, no, I want to take 5 cards and hide 1. And then I will tell you how it works. And after that, it built the demo that I could now use. And then finally, I'll thank the organizers for inviting me, and also to all of you for listening patiently. Yeah, thank you.
On behalf of all the students, I would like to sincerely thank Professor Ramprasad Saptharishi for delivering such an engaging and insightful lecture today. The session gave us a wonderful introduction to beautiful areas of mathematics such as group theory, complex analysis, modular functions, and the Mandelbot set. The interesting examples, including the 5-card trick and the Gilbreth principle, made the lecture both informative and enjoyable. Thank you, sir, for inspiring us with your knowledge and passion.